Yeah, let's continue to the element constraint. The element constraint basically saying what the current through the element and the voltage across the element, how they are related to each other. So today we're going to look at the resistors, capacitors, and inductors. Since the element constraint involves both current and voltage, there's a very important concept. There is the passive sign convention, which is another point that confuse a lot of students. The passive sign convention, why this is important? Because if you don't pay attention to, you may end up with either you have an extra negative sign or you're missing a negative sign, right? So what is this passive sign convention? This is the same as you had in 201. So the passive sign convention is if the current arrow, if the current reference mark, the reference mark basically we use an arrow. If that points into or into the plus of the voltage sign, voltage reference mark, or points away from the negative sign of the voltage reference mark. Right. So let's see if I drew a few. Here I used to poll my class during, I used a clicker when we had in-person instructions, but now we don't have that luxury anymore. So in this case, let's see, I have the whatever the element could be. There could be resistance, inductance, the capacitance, whatever. So in this case, the first one here, we have this arrow, right? This points away from this negative sign. This looks like we are following the passive sign convention for this one, right? Let's see the second one here. The second one here is this arrow actually points away from the plus sign. This is not, this is not following the passive sign convention, right? In the third one here, we have the arrow points into the negative sign. This is not following the passive sign convention either. The last one, we have the arrow points into the plus sign, right? This is the yes. So I hope everybody clear about this passive sign convention. Again, here there's the actual value of the voltage phasor and the current phasor will not affect the passive sign convention being followed or not. Okay, that's one of the probably most confusing part for many students. Although this nothing really mathematically complicated, right? But the concept is really important. Let's move on to the resistance. So let's see if the resistance, if we have the resistance in time domain, I have the voltage across the resistance, and I have the current through the resistance. Now this definitely we are following the passive sign convention because this arrow points into the plus sign of the voltage reference marks. Therefore, we have the Ohm's law, which is the V sub R T should be equal R times I sub RT, right? And if you convert this to phasors, so the phasor, the element constant for the resistances in phasors really straightforward, just as the same R times I sub R phasor. Now, for those who still didn't get the concept of phasor, now in this one here, this current, this one, the voltage current, they be sinusoidal. this one here is just a complex number, right? So whatever the complex number, whatever maybe in the first, second, third quadrant. So this is just a static constant, the number. So the time information completely gone in phasors, right? Or not, in many cases the frequency also gone. So if we draw the phasor diagram, so this is a phasor diagram. The phasor diagram here is you draw the phasor on the complex plane, where the horizontal axis is real axis, the vertical axis is imaginary axis. And you have these two phasors will be in phase. They will be pointing into the same direction because R is a real number, right? R is real number. So therefore, and the real and positive, right? For any practical applications, for practical resistance, you're not talking about the resistance in control. Later, you may into the career, your academic career in MSU here, you may learn, hey, I get a negative resistance in terms of the controls. It could be, but for any really physical resistance, we only have positive resistance. And the real, so they are in phase. If you get a negative, they will be 180 degrees opposite to each other, right? But in this case, we don't have that situation. Let's look at the inductance. For inductance, we remember in 201 we have V sub Lt is equal L di L dt. Right. So in this case, if we change this to phasor, and the first one on the left hand side, that will become V sub L, which is the phasor of V sub Lt. And then on the right hand side, this equation here, now we are calling the property of derivative of the sinusoidal derivative, the phasor of a derivative of a sinusoidal signal, right? So in this case, the derivative of the sinusoidal signal, the phasor of this one is just a j omega times I sub L, right? If the I sub L is the phasor of the I sub Lt. So therefore, then multiply by this L, so we have j omega L times I sub L. So that's the element constant. You see now, the element constant in time domain for inductance is differential equation, and for the element constant for the inductance in phasor is just a algebraic equation. Isn't that beautiful? That's the power of the phasors. So we just magically change the differential equations to algebraic equations. Although the price we pay is we're not working directly with the time domain signals. Now it's kind of abstract. It's kind of, we are wearing a kind of VR goggle now, right? And if you plot these two phasors, so this is a phasor diagram for the inductance. If you plot the phasors, and this phasor V sub L gonna be leading, V sub L leading I sub L by 90 degrees. The reason for that is because the J is equal E to J 90 degrees, right? And omega is positive, L is positive. So you have this 90 degrees angle add up onto this current angle. So if the angle add up to on the phasor on the complex plane, there's a further, so the V sub L is further to the counterclockwise direction, right? So that's what this leading is. This is important. You're gonna have this leading and lagging when you take 320. I know some of you will take 320. So this is the important concept. And all the leading, lagging power factors, all those things are also related to the relative relation of the current and voltage phasors. Okay, let's move on to the capacitance. The capacitance, the equation for the capacitance in time domain is I sub c is equal c dv c dt. Right. So therefore, if we change this to convert this to phasors, and we would have I sub c, the phasor should be equal just as we did for the inductor. So this one, the phasor for this one is going to be j omega v sub c, right? That's the same property of derivative, property of phasor of derivative of sinusoidal signal. So you just multiply that phasor of the original signal by j omega. Right. So in this case, we have a j omega c times v sub c. If we write this, if we write v sub c is equal I times something, just as we did for the inductance, I sub c 1 over j omega c. Right. So that's the element constraint for the capacitance in terms of phasor. Again, here we have algebraic equation. We don't have differential equation anymore. In this case, because 1 over j is equal, the 1 over j is equal 1 over e to j 90 degrees, which is equal to e to minus j 90 degrees. So in this case, 1 over j will add a negative 90 degrees on top of the phasor. So in this case, so the v sub c lagging I sub c by 90 degrees. Or you can see I sub c is leading v sub c by 90 degrees. So this is for the phasor. Or yeah, you can see I sub c is leading v sub c by 90 degrees. Okay, so that's the the lagging and leading concept is really important. That's gonna flow into 320 for sure. Okay, so I'm gonna stop here, and we'll have the fourth clip. I've planned for 3 clips, but it looks like we need the fourth one.